As an excellent tradition of the conference, the 1999 IEEE International Robotics and Automation Conference Committee publishes video proceedings covering new and significant experimental results, demonstrations, and industrial case studies in robotics and automation. The purpose is to enhance and complement the results presented in technical sessions and published in CD-ROMs. Video clips and abstracts were submitted from around the world. This year's video proceedings includes 31 segments grouped into the following 7 categories: Human-Robot Coordination, Novel Robotic Systems, Mobile Robots, Medical Robotics, Virtual Environments in Robotics, Industrial Automation, Robots in Games and Competition. Human-Robot Coordination, a control strategy for human-friendly robots, Australia.
The aim of this project is to develop control strategies for safe human-robot interaction. We are using a Barrett whole arm manipulator. It is a lightweight, cable-driven and easily backdrivable 7 degree of freedom manipulator, suitable for human-robot interaction. Instead of trying to develop a perfectly safe autonomous system, the robot should be viewed as a sophisticated tool. The human operator of the system is responsible to use the system in a safe manner. Therefore, the behavior of the robot must be predictable and intuitively understandable. Autonomous functions are required to make the robot an efficient and convenient tool for the user. In this approach, the basic robot behavior is to compensate for its own weight in a way that is perceived by the user as predictable and non-threatening. This video shows a person safely interacting with the robot. The next stage in the robot's development is to allow autonomous motion to desired goal configurations, while preserving the original characteristics of the zero-G floating behavior. The system strictly limits motor torques in a way that ensures safe operation. Finally, it is planned that the robot will be controlled by a visual interface developed at our laboratory that detects the user's gaze point and facial gestures. When the arm is not actuated, it drops to the table heavily, and the effects of gravity can be easily observed. In this experiment, the gravity constant is increased by 60%. The overcompensation of the gravitational forces makes the robot try to reach a vertical configuration as if the robot was hanging from the ceiling. The small friction with the cable drives makes the robot swing for a while before the friction consumes the kinetic energy and the robot points upwards.
Human-Robot Coordination, Real-Time Stereo Face Tracking System, Australia.
This video demonstrates our real-time face tracking and gaze detection system using a stereo NTSC camera pair and a Hitachi vision processor. The facial model is automatically acquired by first finding skin-coloured regions in the image and then using intensity information to extract templates of the eyes and mouth. Using these facial features, a 3D model is built by stereo matching. This sequence shows real-time 3D face tracking. The 2 images that can be seen correspond to the views of the left and right cameras. The facial features that are being tracked are marked with squares. The system fits the previously acquired 3D facial model to the live video inputs. The system is robust to rotation and translation motions, as well as deformation and partial occlusion of the features. Even when all the features are lost, our system can automatically recover as soon as the features reappear. By using normalised correlation for feature tracking, the system is tolerant to significant fluctuations in lighting. Since the system runs at video frame rate, we are able to track rapid head motions. We visualise the output of the tracking process by animating an artificial facial model. The 6 parameters of rotational and translational motion are displayed next to the artificial face. Tracking errors are less than 1 millimetre and 1 degree for translation and rotation. Our system also detects the position of the pupils of the eyes. The motion of the eyes is visualised in the animation of the artificial face. Detection of the pupil position allows real-time gaze point detection with errors of less than 3 degrees. The next sequence shows our system measuring a user's gaze while looking at numbers on a board.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Human-robot coordination. A cobot in automobile assembly. USA.
The cobot technology from Northwestern University combines intelligent robotic assistance with human force and perceptory senses. This is Scooter, a prototype cobot developed by Northwestern University graduate student and General Motors intern Vitaya Wanasupoprasad. The worker provides the force to move the cobot and its load. The worker is essentially coupled to the passive device through his efforts to move the load. The cobot offers assistance in moving the load, but more importantly, through a software-driven process, it helps the worker guide the load to its final resting spot. Invisible or virtual walls are programmed in. The cobot allows movement only within and along those walls. The wheels simply pivot and redirect worker energy along the invisible virtual walls. There are no brakes on this unit. The programming still allows for the worker to see or feel adjustments needed and provide the force necessary to modify the path of the load. Building on the promise of Scooter, the GM Northwestern team designed and built the world's first industrial cobot, a full-scale prototype cobot-based door unloader for the Pontiac Grand Am. The doors-off process, the first task in the GA Bill of Process, requires the removal of the painted door from the painted body shell in order to simplify the remaining GA assembly tasks. The doors-off tool has 2 primary components, a scooter-like computer-assisted cobotic base and a non-traditional door removal tool. The cobot unloader, like Scooter, demonstrates all the basic cobotic control modes. For example, the door unloader can enforce a circular trajectory on the operator. The doors off the vehicle, the cobot executes an escape trajectory that, for quality purposes, clears the door and the unloader from the vicinity of any Class A surfaces on the vehicle. The operator then drives the unit toward the drop-off station, where the door is carried away to the door trim area for installation of equipment like the glass and window regulator. The door unloader and its predecessors highlight the original goals of the project: to provide the assembly line worker with state-of-the-art assist tools, the ability to mitigate ergonomic problems by providing large, easy-to-hit gross targets, and the potential to impact productivity. These cobotic devices are intrinsically safe. There are no unsafe, powerful motors. Without these motors, the cobots themselves appear less bulky and unwieldy to the operator. Finally, As the system is software-driven, it is flexible and adaptive.
Human-robot coordination. New telecommunication using C-term. Japan.
We'd like to present a new telecommunication system designed to realize a new type of communication. When a skilled operator at an operations center teaches an unskilled worker at a remote site how to use a machine by telephone. Now I'll teach you how to use the device. First, push button alpha on unit A. I got it. Yeah, I pushed it. Next, push button beta on unit B. Well, let me say, oh, God, look, I pushed the wrong button, I think. With this approach, the skilled operator's instructions must be detailed and concrete, and voice-only communication is often insufficient. We'd like to propose a new telecommunication system and thus realize a new type of communication. This is a C-term, which is the core of our new telecommunication system. The C-term is set up at a remote site to assist communication between a skilled operator and an unskilled worker, and it's composed of a rotatable CCD camera and a laser pointer. The skilled operator can observe the situation at the remote site in real time through the CCD camera and make his intentions clear by directing the laser pointer to a particular spot. Moreover, high-cost performance is realized by using servo motors designed for radio-controlled models as the actuators. The telecommunications system at the operations center consists of a headphone with a microphone, a joystick, and a client computer for controlling the C-term at the remote site. As TCP/IP protocol is used for transmitting voices and images, the two locations can be connected through any public network, such as analog telephone networks, ISDN networks, and the Internet. The system at the remote site consists of a headphone with a microphone, a C-term, and a host computer with which to control it. Now I'll teach you how to use the device. First, push this. Okay, I've pushed it. Now push this. Okay, that's done. All right, good work. Communication is smooth and easy without misunderstandings when the C-term is used. This telecommunication system using the C-term provides easy communication and high cost performance.
Human-robot coordination. Development of a 3,500-ton field robot. Australia.
Draglines are large machines used in open-cut coal mines to remove the dirt covering the coal seam. Draglines typically weigh between 3,000 and 5,000 tonnes and can cost up to $100 million. Draglines are electrically powered through an umbilical cable from a portable substation. Each axis of the dragline is driven by one or more 500 horsepower DC motors. The operator controls the dragline with 2 joysticks and a set of foot pedals. The aim of our project was to reduce total cycle time by automating the dig-to-dump-to-dig motion, which comprises about 80% of a typical cycle. Even a small reduction in time will lead to significant productivity improvements and hence cost reductions. Control of the bucket's pendulum swing was the major technical challenge, and visual servoing was identified as the means of controlling the bucket's position. Experiments performed in 1994 by ICRA proved the concept of controlling a pendulum using visual servoing. In 1995, a basic swing control system was developed for a 1/10 scale model dragline. These early successes led directly to the present full-scale implementation project. Our automation system comprises 3 main components: The automation system computer is installed in an electrical control room. The swing angle of the bucket is determined by a laser scanning system located near the boom tip, and the operator's controls are physically moved by servo motors under computer control. Before use, the automation system must be trained. The operator performs a cycle marking the dig and dump points using a button located on one of the joysticks. Intermediate points along the bucket's trajectory may also be marked. When training has been completed, the bucket is filled by the operator and a second button is pressed, starting the automation system. The bucket is moved from the dig point to the dump point and back again following an optimal trajectory and passing through intermediate points marked during training. The automation system relinquishes control to the operator at the end of the cycle, or when a joystick is physically overridden. The operator fills another bucket and the cycle is repeated. The state of the automation system may be monitored by the research team from either the operator's cabin, the electrical control room, or a remote caravan which communicates with the dragline via a radio Ethernet. A major advantage of the automation system is consistent operation, which minimises wear and tear on the machine and provides accurate placement of dirt.
Human-robot coordination. Human-robot interactions. USA.
Human-robot interactions. In this demonstration of robot-human cooperation, a wooden board was transported and hung on a fixed frame. The robot replied to the taps with the answer 0 skillful trajectory stored in its computer memory. The human uses both hands to lead the robot to the frame as they are needed to twist the board. After task completion, the robot reports new skillful trajectory, indicating that the traveled path does not match those, if any, in the computer storage. The robot responds to the taps with the answer 1 skillful trajectory, indicating that the computer had 1 skillful. The robot reported 6 skillful trajectories in memory. As the human starts to lead the robot, he uses both hands for a second. He gradually releases one hand after deciding that the robot is traveling with the board along an acceptable path. The other hand still supports the board to balance the twist caused by gravity. The insert at the lower corner of the screen shows the previous task whose path was stored and now retrieved to serve as a matched trajectory. After the task was completed, the robot reported 6 skillful trajectories, indicating no new skillful ones were added to the memory. The robot found and retrieved a matched path along which it travels. The human interrupts the robot by an impulsive force to indicate that the trajectory is not acceptable. Next, the human signals the robot to continue and leads it to the frame. The robot reports a new skillful trajectory, since the portion after interruption is new. In this demonstration, the frame was moved to a new location through a translation and rotation. The robot requests set start position, since it does not know the new location of the frame. In response, the human adjusts the gripper's coordinate frame to approximately compensate for changes in the frame's location. This has been a brief demonstration for the video conference proceedings. If you are interested in more details, please send us an email.
Human-robot coordination. Dancing with Juliet. USA.
In this video, we show human-robot interaction based on task and posture coordination and control behaviors. The Stanford robotic platforms each have a total of 9 degrees of freedom with a holonomic base and a Puma manipulator. Here, the end effector is held in a fixed configuration while the robot posture is changed. Using the sonar, the robot is avoiding collision by moving in a dynamically consistent fashion to prevent any coupling accelerations at the end effector. Combining posture behavior with object-level compliant motion behavior, we can create a robotic assistant. Our assistant is seen here carrying a load while complying to the gentle guidance of a human. The idea of a robot assistant can be extended to multiple platforms. We are using the wrist force sensors here to fully utilize the higher bandwidth of the manipulators while still benefiting from the increased workspace provided by the bases. A different task and posture behavior allows the robot to dance with a human partner.
Novel robotic systems. Micro-inspection robot for 1-inch pipes. Japan.
A micro-robot for small pipe inspection has been developed. It is 23 millimeters in diameter and 110 millimeters in length. It can be used to inspect pipes 1 inch in diameter. It consists of various micro devices, all of which have been newly developed at Toshiba R&D Center. This is a brushless micro-electrical motor which propels the robot. The torque of the motor is amplified by this planetary gear and worm gear. The robot is propelled by a planetary wheel mechanism. This is a micro-pneumatic stepping motor with high torque. It rotates the camera and the hands. This shows its driving principle, which is based on a wobble motor. This shows a cross-section of the hand. It is made of rubber and is driven pneumatically. This is a micro CCD camera, specially fabricated for this robot. The planetary wheel mechanism can adapt to changes in pipe diameter and also automatically regulates the force of wheel on the walls of the pipe. The flexible rubber link allows the micro-robot to negotiate bends in the pipe. The camera is a high-resolution device with 410 kilopixels, making it easy to detect even small cracks in the pipe. The camera and the hands are rotated by a micro-pneumatic stepping motor, which achieves a torque about 10 times greater than a conventional motor of the same size. The hands bend in any direction by controlling pressure in the internal chambers. The hands are used for recovering small lost objects in pipes.
Novel robotic systems. 1 millisecond grasping system using visual and force feedback. Japan.
This video shows a grasping system using high-speed visual and force feedback. Here, a hand grasps an object observed by high-speed visual feedback. After grasping, compliance control is executed using force feedback. This grasping motion is realized by integrating subtasks such as tracking, reaching, and grasping. Because each subtask is realized by high-speed sensory feedback, the grasping motion has a high responsiveness to dynamic changes in the environment. The system consists of an active vision module, a hand arm, and a digital signal processor or DSP system. The vision module is based on SPE256, a 16 by 16 SIMD processing array with photodetectors. Because each processing element is directly connected to a photodetector, visual processing is executed in parallel. The hand arm is a human-like manipulator consisting of a 7-axis manipulator and a 4-fingered and 14-jointed dexterous hand. Force sensors are installed at each finger joint and at the wrist for force feedback control. These are controlled by the DSP system. It has a hierarchical parallel architecture consisting of 7 interconnected DSPs. As a result, all sensory feedback can be realized on the order of 1 millisecond. By adding other subtasks, the system can perform various different manipulations. As a first example, we show adaptive grasping to an object's changing shape by integrating a pre-shaping motion. Next, we show avoidance of an obstacle during grasping using visual feedback. Avoidance of the obstacle moving at high speed is realized. Lastly, we show tracking control of a grasping object to an obstacle. The distance between the grasping object and the obstacle is kept constant. In future, due to the increasing applications of robots in the real world, high-speed sensory feedback will play an important role in robotic control.
Novel robotic systems. Self-reconfiguration of three-dimensional homogeneous modular structure. Japan.
We have developed a three-dimensional self-reconfigurable structure composed of identical mechanical units. By using many units, a variety of three-dimensional structures can be constructed. This is a simulation of self-assembly of a 56-unit structure. Starting from a box shape, the target structure is formed in a distributed manner. The green-colored units have already reached a position in the target shape. Possible applications include machines used in environments inaccessible to humans, for instance, planetary exploring vehicles or satellite antennae. Transported in a compact folded form, they can expand to their original structure when working and repair themselves if some part becomes damaged. Each unit has 6 connecting arms along 3 orthogonal axes, which can rotate independently, and is designed such that the collection of units can form various 3D structures. The units can change their configuration by using pairwise motion. For example, after disconnecting underlying units, the red unit changes its position and the blue unit rotates about the vertical axis. By repeating this kind of motion, the modular structure can reconfigure itself. In prototype units, rotations and connections are driven by a single motor through electromagnetic clutches. With a span of 26.5 centimeters, the unit weighs approximately 7 kilograms. Each connecting hand has 2 fingers to grasp each other. Rigid connection is realized by sliding cuffs so that one unit can lift another against gravity. Here the video is fast-forwarded to save time. Rotation of an arm realizes the pairwise step motion. The moving unit releases the connection with lower units and is then carried to a different position where it is reconnected. Vertical displacement is also possible, sufficient torque being delivered by worm gears.
Mobile robots. Space Cat. a micro rover based on an innovative locomotion concept. Switzerland.
SpaceCat is the name of the second rover breadboarded product within the microrotor study. It was designed and built by EPFL and the company Mechanics. The robot is constructed by 3 different parts. The first one is the articulated arm supporting the payload. The payload can be rotated 360 degrees around its central axis. The arm can incline forward to allow the instruments to reach the soil. The whole module can also be bent backwards. This movement allows the robot to modify the position of its gravity center at any time. The arm can fold to its initial position, where the gravity center is at its lowest position, assuring maximum stability. The dimensions of the rover are 20 centimeters by 20 for its profile, and 30 centimeters for its width. Climbing over an obstacle can be described in 5 different steps. First, the gravity center is set forward so that the rover cannot fall backwards. The 3-wheel module starts rotating around its center axis and carries the robot on top of the stone. Once the robot is stabilized on top of the obstacle, the gravity center is moved backwards by rotating the arm. The rover now climbs down the stone by rotating again the 3-wheel module. Once the robot touches the ground, the articulated arm is set to its vertical position to reposition the gravity center. Four wheels out of 6 are now touching the surface. This configuration assures the maximum stability. In this sequence, the rover climbs up a more difficult slope. You will notice that the arm is unfolded so that the gravity center is set forward, helping the robot to climb. When the rover is in difficulty, it simply rotates its wheels modules to advance and steps over the stones. If the rover falls over, it can use the articulated arm to stabilize its position. Once the rover reaches the top of the slope, the arm can be folded so that the payload reaches its lowest level. Here is an overview of the system, where you can see the rover being piloted manually using 2 joysticks, or in automatic mode, where the navigation system analyzes the messages sent by the robot and calculates the new parameters that are sent to the different motors of the rover. The user can switch from manual to automated mode at any time, depending on the complexity of the track that the rover has to follow.
Mobile robots. Vision-based navigation system for autonomous mobile robot with error recovery. Japan.
We have developed a robot that inspects the air volume from square air diffusers that are called animal on the ceiling at office buildings. The robot moves automatically, relocating its self-position by recognizing the animal as a landmark with CCD cameras. However, self-position of the robot cannot be calculated. When the robot fails in recognizing the landmark, then the robot stops working. Therefore, we have proposed the behaviors of error recovery and a hierarchical adaptive and learning architecture system, HALOS, that makes the robot to be adapted to the environment by learning so that the robot can continue to work. The structure of HALOS is like this. In HALOS, there are 4 states of the robot. The upper state has more behaviors of error recovery than lower state, so the robot changes to upper state when the error occurs, and the time when the robot changes to lower state is decided by value function. At first, the state of the robot is confident state, but the state of the robot changes to discrete state when an error occurs. In case that the robot mistakes the lure with the animal, the map correspondence action with the small camera is performed to search back and forth. The different size of the landmark is also recognized by the variable template matching method. In case that the robot cannot recognize the landmark by the small camera, the state of the robot changes to reconsideration state. In this state, the main camera that is equipped at the front of the robot is used in sensing. The animal is skipped in case that the main camera sensing is failed too. On the other hand, the animal is found in the main camera sensing. The robot approaches to the animal gradually by the map correspondence action with the main camera. However, the error can occur that cannot be recovered by the behaviors of error recovery. In such a case, the state of the robot changes to reconstruction state. In this state, the robot must relocate self-position to the starting point by the global matching action.
Mobile robots. Gate generation for multi-segment inchworm-like robot locomotion. Singapore.
This video demonstrates the gate generation of an inchworm robot. The robot consists of a series of extensors and grippers. It moves by alternating the extensors and gripper motions. Solenoid actuators are used in the grippers and extensors. The solenoid has on and off states. We use a finite automaton to model the robot motion. State transitions are defined based on the kinematic constraints. The yellow imaginary auxiliary modules are added to the robot for gate generation. To move forward, the head auxiliary extensor is set to on position. The back auxiliary extensor is set to off position. The auxiliary grippers remain stationary within the gate cycle. In single stride motion, 2 extensors move at the same time. The gripper in the middle will be released and move forward. The action will be repeated until all grippers return to the initial state. The same algorithm can be applied to the backward motion. The back auxiliary extensor is set to on position. The head auxiliary extensor is set to off position. The single stride gate is also fault tolerant. The gate generation algorithm can bypass the state of the faulty extensor automatically. The active actuators will drag the faulty extensor, assuming that all the grippers still function well. These gates take fewer steps than the normal one-stride gates. Online gate change can be achieved by resetting the auxiliary extensors to the initial states in the direction of travel. Different gates can be used in various environments. A double stride gate will make the robot move 2 stride lengths in one gate cycle. 4 extensors move simultaneously in this gate. Standing wave gates can be generated. This is the fastest gate because it needs only 2 steps to complete the cycle. All movable extensors are activated. The auxiliary extensors are reset to the initial states after every step. Applications of the gate generation algorithms can be applied to the control of robotic endoscopes for medical inspection and pipe inspection systems.
Mobile robots. Sensor networked robotics. USA.
sensor-networked robotics project focuses on a symbiosis between blind but mobile robots and a stationary environment-based sensor network. We have pioneered several innovations, starting with methods to calibrate a camera network spanning multiple rooms and corridors. A real-time occupancy map is then generated using the sensor network. Since no tracking is involved, the system's reliability and throughput are not affected by the number of dynamic objects. The system is sensitive enough to detect objects as small as human feet. Each blind robot tunes into the occupancy map, being broadcast throughout the environment, which allows them to navigate real-time dynamic situations.
Mobile robots. Reactive navigation in outdoor environments. France.
In easy terrains like the one shown here, the task consisting in reaching a visible goal can be successfully achieved using a reactive scheme. We developed and experimented a visual reactive navigation approach with the robot Llama. The heart of the system is the motion generator that controls the robot on the basis of a visual goal tracker and a local obstacle map computed from data produced by a stereo vision algorithm. Stereo vision is based on the classical pixel cross-correlation algorithm. It computes a disparity map from a pair of images, from which a 3D point image is derived. To compute the obstacle map, the perceived data is discretized according to the geometry of the sensor. On the cells defined, a set of attributes is used to perform a Bayesian classification procedure. The resulting obstacle map is a set of cells to which a probability to correspond to an obstacle is associated. The motion generator relies on a potential field technique. The goal defines an attractive force field, and the obstacles define repulsive force fields. The combination of these forces define a resulting force on the robot that guides it towards the goal while avoiding the obstacles. We have introduced several improvements to the force definitions in order to produce smooth motions. For instance, as can be seen here, the robot is not influenced by an obstacle segment when it is parallel to it. Finally, the goal tracker keeps track on a target using pixel correlation between successive image frames. Special care has been taken on the correlation score determination to ensure that no drift occurs. The motion generator runs at 40 Hz and asynchronously receives the obstacle maps and the updated goal positions. No global map is memorized. The whole system has been implemented on board of the robot Llama, a 6-wheels Massacre chassis equipped with a pair of stereo cameras, a compass, and a 2-axis inclinometer. Here is a typical obstacle avoidance phase. At the bottom left is a video capture of one stereo image, and the bottom right picture shows the motions generated on the basis of the obstacle map. The various algorithms are run on 3 CPUs and are encapsulated into 4 independent modules. Modules are controlled by a supervisor implemented in CPRS, a procedural reasoning system. With this approach, several tens of runs of 20 to 40 meters have been successfully achieved by Llama. This motion mode can be selected by a high-level navigation planner that would autonomously select the goals to be reached.
Medical robots. Laparoscopic telesurgical workstation. USA.
Hello and welcome to a small segment demonstration of the telesurgical workstation of Berkeley, UCSF and Robotics. The first two stills show the master surgical workstation with the components labeled as shown in the still photograph, and the slave manipulator with a gross motion stage and a fine motion stage as shown in the second still. We'll discuss these components as we go into the videotape to follow. The first segment of the videotape shows the insertion of the slave manipulator into the belly of an anesthetized pig at the UCSF Animal Laboratory. 3 surgical residents are in the background. The one on the left will perform the procedures to follow. Matt Danning is the technician inserting the robot inside the pig. The surgical resident in the middle will be the manual instrument holder, and the other person is the camera holder. The next still here shows the operation in progress. The master manipulator is held by the surgeon on the left, who's operating a full 7 degree of freedom customized Phantom. The slave manipulator is suspended over the side of the pig with the slave manipulator entering the patient. A manual instrument is being used by the surgeon in the middle of the picture, and the camera operator is on the extreme right. The surgeons had not seen the instrument before it was brought into the laboratory, so this was the first time they were learning to use the instrument, and they learned on the fly, so to speak. Here's an internal view of the instrument in action. This is the wrist degree of freedom of the slave manipulator, showing the roughly 270 degrees of freedom available for insertion. The procedure that the surgeons tried was Nissen fundoplication, which is a procedure used for strengthening the sphincter entering the stomach to prevent reflux. We particularly chose this procedure to show that we could in fact exert enough forces to allow for the needle to be entered into the rather muscular stomach wall, which is what you're seeing in this chunk of the videotape. You see that there's more than enough force to drive the needle through the stomach wall and for it to emerge on the other side. There was certainly enough dexterity to be able to grasp and re-grasp the needle as shown in this particular segment. The next segment of the videotape will show the act of throwing a suture in the stomach wall. The act of suturing involves using the master manipulator to be able to thread the needle through the stomach and to retract it onto the other side. Again, the procedure that was performed at UCSF involved the full-scale Nissen fundoplication, and what you see here is just 1 or 2 sutures. This is the first suture, and in the next segment of videotape you will see a couple of knots being thrown. In order to perform the knotting, we had to use a manual instrument, which was operated by the second intern. That's the instrument you see on the left. And in this procedure you'll see first the first knot being thrown, and some things to note are that this version of the prototype instrument was first of all unimanual. The second version of the instrument will, both the left and the right hand instruments will be operated by robot, and unlike this one where the instrument on the left was manually operated. Also, the robotic instrument will be more tapered like the manual instrument that you see on the left. The first knot has now been thrown, and this last piece shows how it is possible to easily throw a second knot as well. This version of the experiment was performed a couple of times in the animal laboratories. The results were satisfactory. There was some feedback in terms of the psychophysics of use of the instruments, and these have now been taken into account in the design of the second version of the workstation. We have now received preliminary FDA approval to begin trials in human patients as well. The research has now gone along, and this we expect to have our bimanual version before the end of 1999. The research has been supported by NASA, the National Science Foundation, and the Office of Naval Research.
Virtual environments in robotics. A virtual excavator for operator training and controller evaluation. Canada.
Research carried out in the Robotics and Control Laboratory at the University of British Columbia addresses issues of control of excavator-based machines. A simulated virtual excavation environment has been developed as a tool for operator training and the development of human interfaces and teleoperation strategies. The simulator includes a graphically rendered visual environment, a force feedback joystick that allows the operator to command excavator motion, and a digging model that allows the operator to experience bucket interaction in real time. Two haptic devices have been employed as an operator interface, namely the maglev joystick, a 6-degree of freedom rate control device, and the twin pantograph, a 5-degree of freedom large motion interface. The digging and payload forces that they reflect to the operator are synthesized using the simplified dynamics of a real Takeuchi mini excavator and a novel dynamic model of bucket soil interaction. Previous soil interaction models have provided only limited static simulation results. The digging model assumes a flat cutting surface that moves through the earth as commanded by the human operator. The resultant estimated forces and torques are the combination of viscous and Coulomb friction, as well as soil stiffness, soil shearing, and load accumulation effects. The visual environment includes a scale model of the mini excavator and is rendered by a silicon graphics workstation. A graphical user interface allows the user to select a variety of viewpoints that aid visualization and control during digging. Visual environment deformations are also rendered, clearly showing excavated trenches as they form. Perception of the bucket height and its distance from the ground plane is aided through the use of a bucket shadow. The simulator has provided a realistic enough environment for evaluating a new variable impedance control method, as well as automation strategies for excavator-based machines. Plans for future work include the modeling of non-homogeneous ground environments that may include submerged objects, such as pipes and rocks, thus making it ideal for operator training.
Virtual environments in robotics. Interaction with simulated environments using a magnetic levitation haptic interface device. USA.
In the Microdynamic Systems Lab at the Robotics Institute of Carnegie Mellon University, we have developed a new haptic interface device based on magnetic levitation. The device and all amplifiers, processing, and power supplies are contained in a single desktop height cabinet. The range of motion of the floated handle is 25 millimeters in translation and 15 to 20 degrees in rotation. Its maximum stiffness is 25 newtons per millimeter at a 1000 Hertz servo control rate. Motion can be allowed or constrained in any direction. The moving part of the magnetic levitation device is a thin hemispherical shell with 6 embedded actuator coils and a handle. Permanent magnet assemblies are fixed on either side of each coil. 3 position sensor assemblies focus light from LEDs in the floating shell onto position-sensing photodiodes. The magnet and sensor assemblies are mounted in an outer aluminum shell set into the top of the device cabinet. The magnetic levitation haptic interface device can be used with a workstation as a combined haptic and graphic interface for simulated environments. Simple simulations can execute on the local control processor, using the workstation for display only. In this simulation, the user feels corner, edge, and face contacts between the inner cube and the outer wireframe cube. The 75 Hz small motion bandwidth and the 5 to 10 micron position resolution of the device are sufficiently high that realistic surface effects can be emulated. Here, each quadrant of the displayed surface has a different friction and texture. Impact dynamics are also simulated. More complex dynamic simulations execute independently on a workstation and exchange tool position set points with the local controller through an Ethernet network. The simulated tool and the actual haptic interface device position and orientation are coupled by stiffness and damping gains. Objects in this simulation are manipulated with a paddle-shaped tool. The user can strike, push, pick up, or throw and catch objects in the simulated environment and feel the computed dynamic response of the tool. The simulation models physical dynamics, performs collision detection, and evaluates motion constraints on all the objects in the virtual environment in real time at an update rate near the position bandwidth of the haptic interface device.
Virtual environments in robotics. Interactive design of a virtual factory using cellular manufacturing system. USA.
At the Virtual and Synthetic Engineering Laboratory at SUNY Buffalo, we are investigating the applications of VR in the design of factories of the future. We have modeled a virtual factory which presently consists of several machines, robots, and human operators. The goal of the project is to design and test and improve manufacturing facilities before a physical prototype is built. The input to the virtual factory is presented through a novel 3D virtual matrix interface where the user can input part machine process information interactively. Next, a cell formation algorithm called the modified Boolean method is applied to form groups. In this case, the algorithm returns 3 different groups. This matrix can also be rotated in a 3-dimensional view, and we can see that in the Z direction, the machine loading information is provided. Once this information is read, the user can now change operation from machine to machine and also remove exceptional elements. Now this information is provided into a top view of a virtual factory where the user can pick a whole group of cells and move it around from room to room and within a factory. In this case, the intersection algorithm has been disabled. The user can also pick one machine at a time and place it wherever he or she desires. In the immersive front view also, a whole group of machines or an individual machine can be manipulated within this virtual factory. Here the user is seen moving a robot to a more convenient location. The entire virtual factory has been modeled in a virtual environment on an Onyx 2 silicon graphics machine. Designer can fly through and walk around the factory by wearing a stereo head-mounted display, and by using instrumented gloves, the user can pick and place the machine intuitively. Apart from the factory design, we can also use the factory to study ergonomics, facilities planning, and maintenance planning of the factory in a very efficient fashion. In this project, we have demonstrated that high-power graphics coupled with mathematical algorithms for factory design can provide powerful tools for improving the manufacturing plants in the future.
Virtual environments in robotics. Design of virtual objects for exact collision detection in virtual reality modeling of manufacturing processes. USA.
We introduce a concept of virtual objects which extends applicability of exact collision detection algorithms to non-convex objects at real-time interactive speeds. We are designing an automated procedure to encapsulate into virtual objects the surface patches of interest for collision detection. Our approach is illustrated with a manufacturing process. Coordinate measurements are performed on a centrifugal pump using a coordinate measuring machine. Note that this part has a number of non-convex regions where it is difficult to design accurate collision detection techniques. The key notion in our approach is the creation of virtual objects associated with specific virtual reality scene objects and testing collision between virtual objects instead of the original scene objects. We perform triangulation inside a CAD environment, ProEngineer in this case. Cave and Immersidesk virtual reality platforms developed at UIC using silicon graphics processors are used for the implementation.
Industrial automation. Design and performance testing of the sensors with soft contact surfaces having 8 sensing cells. Yugoslavia.
New sensors with 8 sensing cells mounted on the fingers of a parallel gripper enabling measurement of all relevant components of external load in various tasks realizations have been presented. Reflexive optocouplers are mounted on a separate plate enabling easy disassembly. 4 optocouplers for measurement of normal force are mounted in corners, other 4 for tangential forces between them. External load deforms the sensor's elastic body. This deformation is detected by optocouplers measuring the distance between the optocoupler and the corresponding reflexive surface in each direction. This animation schematically shows sensor behavior when normal force, tangential force in 2 mutually orthogonal directions, torque, and composite load are applied. The sensors are very sensitive and they are able to detect force of small intensity produced by human breath as well as position of force acting point. In this experiment, the contour of elastic band is followed by a plastic straw preserving very low contact force. Trajectory is controlled by minimizing tangential force while preserving normal force within predefined range. This algorithm ensures that the sensor's grasping surface is permanently tangent on the local contour shape while advancing along the contour. The contour is successfully followed even if the profile is not smooth. In case of singularity, here in the corner between the 2 fingers, an additional tangential force occurs and the robot stops advancing. The gripper rotates till contact force becomes orthogonal to the grasping surface again, and then advancing along the contour continues. In this experiment, on the basis of sensor information, the probe follows a planar slot of rough surface quality. The slot is of unknown and very irregular shape with a variable inclination.
Industrial automation. Distributed control of flexible transfer system using learning automation. Japan.
We propose flexible transfer system called FTS as one of a distributed autonomous robotics system. FTS is an advanced type of transport system in flexibility and robustness. In this video, we will show the experimental system of 3x4 modules and show that the adaptive transfer paths can be formed from random state in the fully distributed way. FTS is composed of many autonomous transfer modules. Any 4 sides of the module can be connected modules which can communicate through Ethernet. The direction of a pallet transfer is restricted to modules in the XY direction. Each module has 8 omnifields and it transfers a pallet to the neighboring module. Each module has 2 proximity switches. When the module recognizes a pallet with proximity switches, it will complete pallet transfer by stopping omnifields. Next, by computer simulation, we show the motion of a pallet transported by modules and a strategic vector on each module. FTS has multi-layered strategic vector fields for the transportation of a pallet by each task. Each module has action strategies. They are defined as vector value. Local interactions among the modules develop the global stochastic vector field, and it corresponds to a particular task. These vector fields are updated using learning automata, and optimal paths are generated. At initial state, 4 vector values on each module are almost equal, and pallets are moving around randomly. After passing enough time, some vectors have a particular direction, and optimal path is generated. Pallets are moving smoothly, following the yellow arrow that shows the transportation path. Next, we set up port 1 and port 2 on an experimental machine of FTS, and its task is to transfer the pallet between these ports. At initial state, pallets are moving randomly. Because modules don't recognize their correct position, they cannot explicitly know what is the correct behavior. They are learning the correct direction for transportation as strategy vector by learning automata. Red arrows mean the path of a pallet marked with a red cross in a circle. After 20 minutes, modules can transport pallets on feasible paths. But in the past, there is a case that module for transportation of the pallet is occupied by another pallet, and it is necessary to avoid collision. So this passes cost more time than optimal one to transport pallet. After 16 minutes, pallets are moving to each destination in no crossing path. A red arrow shows the path to port 1, and a blue arrow shows the path to port 2. Pallets are moving in optimal paths, avoiding a collision with other pallets. In this way, the strategic vector field for an optimal transfer path is generated by learning automata, and a flexible transfer system has been self-organized.
Industrial automation. Impedance-based assembly. USA.
Vehicular transmission components, such as this forward clutch and planetary gear reducer, are representative of a large class of assemblies that are still performed manually because conventional automation is unsuccessful. Under position control, automation will fail if the position uncertainty exceeds the tolerance for successful assembly. To emulate the success of manual assembly, robots must behave compliantly. The experiments shown here were conducted on an Adept 1 robot retrofit with an open architecture controller. Our control implementation is a flavor of impedance control that we call natural admittance control. In this technique, a model of a robot, incorporating estimates of actual inertias, is simulated in real time to respond to sensed end effector forces plus virtual forces defined with respect to a computed attractor. The physical robot is servoed to track the idealized simulation. For the forward clutch example, there are 5 toothed rings with a possible radial misalignment 7 times larger than the assembly tolerance. We performed this assembly task successfully using a blind search in the XY plane and in Z rotation while exerting a steady, gentle downward Z force. The uncertainty is thus accommodated with the robot's programmed compliance. One simple and often successful technique for invoking compliance is the use of a passive remote center of compliance wrist. However, we found passive compliance to be inadequate for assembling the planetary gear set, even when used in combination with implicit force control, as shown in these trials. Assembly attempts were unsuccessful in 50% of the trials due to jamming. Using natural admittance control, reliable assembly was achieved with a mean time of 11 seconds. Due to force responsiveness, natural admittance control reduced the frequency of jams and was able to recover when jams did occur. Our defined virtual attractor interfaces well with the lower-level natural admittance controller to command search patterns. In addition, the attractor can provide a bridge to higher-level planning. The task shown here is an abstraction of a more complex assembly in which planning is required. The goal is to guide a key-like peg through a stack of layers, each with a characteristically shaped hole and each able to slide in the plane. For each layer, the compliant robot, guided by a virtual attractor, invokes a rectangular search to align the peg's key with any slots. After descent, we perform layer identification to distinguish the type of hole. In the case of a jam, the controller replans its strategy based on previous decisions and layer information, and executes the strategy via commanded trajectories of the virtual attractor. We conclude that the use of natural admittance control and virtual attractors expands the capability of robotic assembly while providing an effective bridge between low-level dynamics and higher-level planning.
Industrial automation. Coordination of multiple mobile platforms for manipulation and transport. USA.
We have developed a small team of heterogeneous robots which cooperatively grasp objects and transport them in a partially structured or unstructured environment. In this program, you will see a TRC LabMate equipped with a passive arm, a TRC LabMate equipped with an active force-controlled arm, and a Nomad XR4000 equipped with a stiff position-controlled forklift. 2 robots are used to move objects of different geometry and mass. The platforms can perform turns to avoid obstacles. When picking up an object, communication between the robots is critical. The compliant force-controlled arm pushes the object onto the lift. Upon completion, the XR4000 picks up the object while the compliant arm constrains it. The two robots secure the grasp by applying a preload before beginning the motion. With 3 platforms, our system is also capable of carrying flexible objects such as a board. In this example, the center platform helps to support the board and the object. A critical aspect of the system is the compliant force-controlled arm. The rear platform is equipped with a novel forklift-like arm which possesses intrinsic mechanical compliance. This is achieved by incorporating linear springs in a parallel 3-degree of freedom manipulator. The spring extensions are adjusted in real time using a position control system to achieve the desired link stiffness. Therefore, a Cartesian endpoint compliance of the entire arm can be easily changed. Because the arm is compliant, a mobile robot can manipulate or interact with stiff objects not precisely positioned in the environment. Another important feature of this system is the ability to transport objects without special purpose fixtures. We use palm-like end effectors to grasp the object and maintain force closure by coordinated control. The coordinated control of the team is achieved by designating 1 or more leaders. Each leader plans its own path based on sensory information, and the followers are responsible for maintaining force closure and avoiding collisions. The communication is possible through a wireless peer-to-peer network, sending packets at a precise interval. In the 2-robot formation, the trailing platform follows the lead platform like the rear wheel of a bicycle. The front wheel or lead platform steers while the rear wheel or follower platform trails behind at a fixed distance. Similarly, in the 3-platform example, a tricycle analogy can be used. In conclusion, we have developed a system of multiple coordinated mobile robots. Multiple heterogeneous robots are able to coordinate and transport objects around obstacles even with platform errors and disturbances. The key features that make the system successful are an architecture and communication scheme that allows the robots to cooperate, simple planning algorithms based on the bicycle or tricycle model, and an actively controlled compliant arm that accommodates errors.
Industrial automation. Weightlifting motions for a Puma 762 robot. USA.
The goal of the project is to extend the payload of a Puma 762 beyond its 45-pound limit set by the manufacturer. To demonstrate our results, we tried to find the largest weight that the Puma could lift from the downward posture shown to the upward posture. First, we swing a 45-pound weight by moving joints 4 and 5 of the Puma. This is the maximum rated payload of the arm. Next, we attempt to move 90 pounds on the same path. The attempt fails, demonstrating the 45-pound limit. We then solve the optimal control problem to find the path that maximizes the payload. It was solved by gradient method starting from an initial feasible path. Note how in this case, energy is pumped into the system during the swinging motion. This solution lifted a maximum of 70 pounds. When more degrees of freedom are added to assist in the motion, the individual joint torques are reduced. In this case, we allowed all 3 wrist joints to move. We'll see the motion again to observe the wrist going through a singularity. While moving through the singularity, some joint torques are reacted by the structure and not the actuators. Finally, we allowed the algorithm to vary all 6 joints. We found several local minima to the nonlinear optimal control problem. For our first solution, the Puma lifts 115 pounds. Again, we see the path move through a singularity. The second solution lifted a maximum of 125 pounds. For our best solution, the Puma was able to lift 145 pounds. This increased the payload capacity of the Puma by more than a factor of 3. Again, we'll see the Puma more than triple its payload capacity.
Industrial automation. HiLab, a high-level system for generating, representing, and evaluating assembly sequences. Germany.
The goal in robot assembly is to build a mechanical product which can be assembled by robots. A high-level assembly planning system generates sequence plans specifying the order in which parts are to be assembled and computes the trajectories to bring the parts together. The high-level assembly planning system HiLab, introduced in this video, uses geometric and physical reasoning to find an optimal plan. HiLab also provides a new approach to assembly stability and a user-friendly human-machine interface. The assembly components are represented as CSG objects. A set of symbolic spatial relations define the topology of the assembly. Here the user defines a sharp-fits-hole and a face-against-face relation. After the definition of all symbolic spatial relationships, the user checks the topology with HiLab's animated exploded view. Here a motorcycle engine consisting of 27 components is shown. The user defined the topology using symbolic spatial relationships as illustrated before. The system automatically generates and evaluates all valid assembly sequences basing on the assembly by disassembly philosophy, considering local and global assembly constraints like connectivity, geometric feasibility, and assembly stability. The optimal assembly sequences are stored as hyperarcs of an AND/OR graph. HiLab provides a new approach to assembly stability. The set of stable orientations, marked red, is calculated with the linear programming methods and is projected onto the unit sphere. With increasing stability on the unit sphere, the costs assigned to the assembly operation are decreased. The output of HiLab is an optimal assembly sequence plan, which is used to program robots automatically. We used the robot simulation system IGRIP from DNAP Robotics to simulate the sequences. Stäubli animation robots are used to execute the assembly plans in real world. HiLab automatically generated and evaluated the sequences, trajectories, grasps, reorientations, and other criteria out of the user-defined topology of the assembly.
Industrial automation. 3D CAD data-driven assembly robot cell system. Japan.
From Rico and Hashimoto Laboratories' endeavors has come a prototype CAD data-driven system called the Autonomous Assembly Robot Cell System, ARC. The primary features of the system are controlled by 3D CAD data and assembly model data, external environment recognition by the hand-eye system, assembly task planning using assembly model data, automatic generation of robot task programming. Here, multiple robots are given assembly task assignments using an assembly model. A developer unit for a Rico copying machine consisting of 25 parts was used for this simulation. The number of robots required and the takt times were calculated based on the desired production quantity for the day and the robot's operation time. Now for planning of each robot's sub-assembly sequence. As seen here, a sub-assembly consists of 9 parts. A possible assembly sequence model is automatically generated from the liaison collision graph analysis using PetriNet. From this model, the optimal assembly sequence is ascertained on the basis of assembly cost, as calculated by the robot simulator. In this case, assembly time was used for evaluating cost. Robot task program modules, some of which are stored in the robot simulator library, are configured according to the assembly sequence planning. The values of the variables for the program modules are obtained from the 3D CAD and assembly model data, from which the task programs for the assembly process are derived in the virtual environment. The robot examines the dispersion of the assembly part's position and orientation via the hand-eye system, which measures the range image with a laser rangefinder. In order to recognize the component parts and their positions and orientations in the workspace, product feature models are needed. This is provided by the surface sampling data of the model, which is contained in the 3D CAD data. Position and orientation can be ascertained using the ICP, or Iterative Closest Point algorithm. As demonstrated here, the ARC system is capable of autonomously performing assembly task assignments and sequence planning from product model and assembly model data.
Industrial automation. Folding cartons with fixtures. USA.
We present a flexible method to fold cardboard blanks into cartons by moving them through a fixture. These cartons have self-locking tabs and are used for product packaging. Our implementation uses an Adept-1 robot to move the carton through the fixture. Fixtures for different cartons can be interchanged for rapid product changeovers. A fixture is designed for a given carton and a selected carton folding sequence. The fixture walls fold the carton panels as the carton is translated in contact with the fixture. We now demonstrate the folding of a carton with a fixture. The robot uses vacuum suction cups to hold the carton and executes a sequence of folding operations. Here, folding is performed in 2 stages, with the rotation of the carton between them. The fixture is equipped with 2 pneumatic actuators to aid the folding. The folding sequences are generated by a motion planner that models a carton as a manipulator arm with rotary joints and branching links. Each folding sequence corresponds to a path from the carton's initial configuration to its goal configuration. The folded carton is ready for insertion of the product.
Robots in games and competition. Beach ball volley playing robot. Japan.
Future robots are going to work in your houses and hospitals with humans. Toshiba has developed a beach ball volley playing robot as a demonstration of such a human-friendly robot technology. We consider that it is essential to interact with robot using everyday words such as, "Let's play volleyball." For the everyday word commands to work, the robot needs to measure the target's relative position with respect to the robot position, to know the mechanics and procedures of the tasks, and to have a good database for the environment and the target. With an integrated sensor feedback technology, we have demonstrated a robot which can play beach ball volley with an opponent, pick up a ball from the floor, and shake hands with a human by only one respective everyday word command. The robot uses 2 head-mount CCD cameras to measure the target ball position in every 1/60th seconds. The cameras always track the ball. The operator commands the robot to pick up the red ball. Then the robot starts to search for the red ball on the floor. After finding the ball, it moves above the red ball. Then it checks the arrangement of all the balls to make a plan to pick up the ball. When the robot finds that the arrangement is too difficult to pick up the red ball, it pushes the green ball aside and checks the ball arrangement again. Then it picks up the red ball. We use visual servo control at the rate of 1/60th seconds to achieve this picking up motion. This is the robot view. After pushing aside the green ball, the robot checks the arrangement again and approaches the red ball by using the visual servo control. Also, to show the human friendliness of the robot, it can shake hands with a human. It has a tactile sensor in its right hand to start handshaking. It also has a 6-degree of freedom force torque sensor at its wrist to readily respond to the young lady. See you.
Robots in games and competition. Autonomous firefighting mobile robot competition. USA.
This video introduces the Trinity College Firefighting Robot Contest. In this contest, autonomous robots navigate through a maze, find and extinguish a candle in minimum time. Each robot has 3 runs, and the score is computed from the best 2 runs. Deductions are given for reliability, non-dead reckoning mode, returning to starting position, and obstacle avoidance. In 1998, the contest drew more than 70 robots from the US, Canada, and Europe. Contestants included university professors and students, engineers, high school students, and even junior high school students. The maze measures 8 feet by 8 feet and has 4 rooms with connecting hallways. The candle is placed at random in one of the rooms. The 1998 winner is Phoenix, shown here, built in the Robot Engineering Lab at Trinity College. Infrared ranging sensors on Phoenix enable non-dead reckoning operation via wall following and edge detection. Raptor, shown here, was designed at Central Connecticut State University and was the 1996 contest winner. The contest encourages innovation by inventors of all ages and affiliations, and it provides an ideal medium for teaching engineering design.
Robots in games and competition. Robot soccer system for Narrowsot. Korea.
This video shows 2 soccer robot teams, Best and Y2K2, and a demo game between them. The FIRA Robot World Cup France 98 in Paris witnessed the smallest robots ever to play the game of soccer between the Y2K2 and the best teams from Korea. It was the Narrowsot category with the robot sized 4x4 by 5.5 centimeters. In the Narrowsot category, only the vision information is used as a feedback, and there are no internal sensors such as encoders within the robots. Due to this, precise and fast robot control is difficult. Instead, cooperation and coordination among robots are very important in Narrowsot, as there are 10 robots on the playground. The robots of Best Team is 3.75 centimeters cubic and have H7C51 microcontroller and 2 DC motors without encoder and RF communication module. The Best Team is designed with 2 DC motors, fixed in parallel due to small size. A 3-level hierarchical scheme for visual servoing, target generation, and role allocation constitutes its control structure. Dynamic role allocation is done in the highest layer, that is, in the role allocation layer, as per the context and role importance. This shows our simulator for tactics. A 2-to-1 formation is normally adopted to. One of the defenders is assigned to attack as libero when the 2 attackers are blocked. The Y2K2 team uses 2 centrally aligned wheels, which are easier to control. 9.6-volt rechargeable cells are used for power supply. Although the same color patches are used, the robots are distinguished by robot position tracking. 2 actions are defined for the robots to follow in the vector field and to shoot. Under normal conditions, robots follow the vector field. The action selection layer selects shoot action when it is in a good position to do so. A 2-to-1 formation tactic is used as a zone defense scheme. Let us watch a demo game between the yellow color best and the blue color Y2K2 teams. The best team is kicking the ball. The ball is passed to Y2K2 goal area. The robot at the center shoots the ball. The other robot shoots the ball again and scores a goal. The best team robot shoots the ball again, but the Y2K2 goalie blocks it. The ball runs into the other side of the field. The Y2K2 starts attacking. The Y2K2 robot passes the ball to the center of the goal area and scores a goal. This video showed 2 nanorobot soccer systems, the best and the Y2K2. The best used 3-layered controller which is hierarchical in nature. Role allocation and libero strategies are used by this team. The Y2K2 is designed with an action selection layer and it used a fixed role allocation scheme. The narrow search system is a good benchmark for the multi-robotic system research. Thank you.